Hello. In this video, I want to talk about higher order partial derivatives that we could take. So let's get right to it. Okay. So if you have a function that has two variables, x and y, you have two choices for taking partial derivatives, or at least two choices for the first partial derivatives you can take. If you want to take higher order derivatives, which means like repeatedly take derivatives, each time you take a derivative, you have a choice. Do I want to take the derivative with respect to x and y? So if you're talking about all second partial derivatives, there's going to be four of them. Even more if you have more variables. So if you have three variables, then you have three choices at each step. So you would have nine second partial derivatives. Okay. Think about notation. So with the subscript notation, when you take more and more partial derivatives, you're going to take the newer derivatives to the right. So you kind of read it from left to right. If you're taking derivative with respect to x twice, then it doesn't matter which way you read it. But if you're mixing the variables when you take the derivative, taking derivative with x first, then y next, you'd read it this way from left to right. This would be the opposite direction. You take the derivative with y first and then followed by x. If you're using Leibniz notation though, so if you're doing df dx or with partial derivatives, you do the curly del f del x, then the newer derivative comes to the left of it. So unfortunately, there's this weird switch of the order. With this notation, on the bottom, you're going to read from right to left. So if you first compute del f del x, and then you take del over del y, so the derivative with respect to y, you write the derivative operator to the left. So you're going to write it this way, del y del x in the denominator, and that means you take derivative with x first, then y. So you're reading it in the opposite order. And same down here. Okay, so that's confusing. I'm sorry it worked out that way, but I didn't make it up, but you should know, so it doesn't get confusing. Okay, let's do a couple examples. Let's see, so here are some examples that we worked on last time. So I just kind of copied over the first order partial derivatives. So if I want to compute fxx, I look at this guy and take the derivative with respect to x again. This function doesn't have any x in it, so it's constant with respect to x. Derivative is just 0. So if I'm computing fxy, that means I take fx and take the derivative with respect to y. So I just use the power rule there, 3y squared. Fyx, that means we're going to take the function fy, and then you take the derivative with respect to x. So derivative with respect to x here, you can view this as x times constant with respect to x, so just 3y squared. And fyy is going to be this guy with respect to y. So I'm going to just use the power rule on y, square y squared, and get 6xy. Okay, so I made this big deal about how the notation and order matters, and then I guess we have an example where the mixed partial derivative turned out to be the same. Is this a coincidence or is this a pattern? So let's do another example and see if it comes out the same way. Okay, so hxy is going to be this function, and I'm taking the derivative with respect to y. So derivative of this guy, derivative of sine is cosine. Leave the inside alone, and then I multiply by the derivative of the inside with respect to y. So derivative of xy with respect to y is just x. And for the second term here, I'm going to use product rule, thinking of this as two functions that way. And I'm going to take derivative of each of those with respect to y using the product rule. So derivative of xy is x times cosine xy plus xy times the derivative of cosine. It's negative sine xy. And then by chain rule, I'm taking derivative with respect to y, so I get x left over. I guess I could simplify this a little bit. The first two terms are the same, so 2x cosine xy. I can just collect those. And I can pull the negative sign to the front. There's two x's, so negative x squared y sine xy. Okay, let's do the hyx. Okay, so this time I'm gonna take this guy and take derivative with respect to x. So I'm gonna use product rule that way. Derivative of x squared times cosine xy plus x squared times derivative of cosine is negative sine xy times y. Just rewriting it. And again, we get that the mixed partial derivatives turn out to be the same. Is this always the case? Almost always, yes. So there is a theorem called Claret's theorem. So it turns out that it is possible to come up with a counterexample where the mixed partial derivative does not match. But most of the time it does. So there's two things you need to worry about. Let's say this is the domain. The point at which you care about the mixed partial derivatives have to be at a center of some disk. Okay, so it cannot be on the edge. So if it's in the kind of middle of the domain, then you can find at least a small disk around it. And then on top of that, on that disk, the second partial derivative have to exist. So it has to be differentiable twice. And they have to be, the derivatives themselves are continuous on that disk. So as long as it's not on the edge and there's no funky things happening with the second derivative, there's no division by zero or anything like that, then they're gonna agree. So pretty much most of the time, they're going to agree. Now, I had to talk about this business of not being on the edge and it has to be continuous, but this technical detail is kind of out of scope for this class. So I am not going to give you a trick question where this does not work. So most of the time you could just, so actually in this class, all the time, you could assume that hxy is going to be hyx or f for that matter. So knowing this theorem, this saves you 25% of the work, right? If you're computing four second partial derivatives, you just got, you have to compute the fxx and fyy. That's going to be most of the time unique, the different function. But fxy and fyx, if it's a mixed partial derivative, you could assume that they're the same. So you just have to compute one of them and then be done with it. Okay? So that's a handy theorem to know. Okay, so I think this is where I want to end this video. I'll see you later.